is bending. And we know that when we're talking about concavity, we're often looking at the second derivative. So to review some stuff that we saw last unit, coming from that chart, we know when the second derivative is certain like signs, then we know that we can look at the function and how it's bending. So when the when the second derivative is positive, we know that that is when the function is going to be concave up. When the second derivative is negative, we know that that is when the curve is going to be concave down. When f double prime is 0, I'm going to think of this as just neither concave up nor concave down, which can look several different ways. So like an example of something that would be neither concave up nor concave down would be like a straight line. A linear function has no concavity. Even if that linear function is horizontal, still no concavity. Other cases where we'll have a second derivative that's equal to 0 is if I think of like a cubic function. We can see in the cubic function that it first starts off being concave down, and then it switches to be concave up. That instance where the concavity is switching is technically also going to have no concavity. There's going to be a split instance where it's not concave up, and it's also not concave down. If f double prime of a is undefined, then there's different things that could happen, like probably the first derivative could be undefined, or maybe even the function itself is undefined there. So the easiest way to kind of summarize when I say f double prime is undefined is we're going to say f of x is not twice differentiable, meaning it just doesn't have a second derivative at x equals a. Differentiable, if I can spell. And then this last one is something that we did not include on that chart from unit 2. So really of everything that's new, I think we know everything in those first 4 rows. This 5th row is going to be something different. And if I say f double prime changes signs, then f of x is going to have something called a point of inflection. At x is equal to a. So if I go back up to that example I did talking about where the second derivative is equal to 0, that point where we had no concavity, where it was switching to be concave down to concave up, that would be a point of inflection. I'm just going to abbreviate that as POI. And I know that that's a point of inflection because on one side the second derivative is less than 0, and then on the other side of the graph the second derivative is greater than 0. So whenever we're talking about where specifically the concavity is changing, we are going to call that a point of inflection. So what we're going to be focusing on today is like first off identifying, just like we did for intervals of increasing and decreasing, the intervals of concavity. When is the function concave up? When is the function concave down? But we'll also add to that, can we identify where a point of inflection is going to show up at looking at the graph algebraically. So I do want to go ahead and define point of inflection again. So point of inflection, other things you can call it, POI, common abbreviation. You can just say inflection point. That last spelling of it, that's actually the British English spelling of it. So if you look it up online and see that, you're probably looking at a British website, but they all mean the same thing. And the definition of a point of inflection is where the second derivative changes sign. And so often when we're looking for a point of inflection, we'll still need to look at a sign chart so we can actually see when is the second derivative positive and when is that second derivative negative. So the steps for this is going to be, like I said, very similar to what we saw yesterday. We're going to need to find a derivative, but now since we're talking about concavity, we'll have to find the derivative twice, like find the first derivative and then find the derivative of that to get the second derivative. Find the key points of it and then make a sign chart and use that to justify our answers. So yesterday I kind of gave you like the steps and the big idea. I'm going to do the same thing for this one. So the second derivative again can tell us certain things. So we want to talk about like the big idea, how we justify our answers, and then the steps that we're going to be looking for. Make that a little bit bigger. So if our function is concave up, the reasoning we're going to use a function as concave up is, of course, when the second derivative is positive. So your function will be concave up if f double prime is greater than 0. Your function is going to be concave down when f double prime of x is less than 0. And then the point of inflection is going to be where the second derivative changes sign. So whether it's changing from negative to positive or positive to negative doesn't matter, but it's going to be where f double prime changes signs. So big idea, if ever I ask you to find concavity, the big overall calculus idea we're talking about is we want to look at the sign of the second derivative. Or if you're looking for a point of inflection, you're really looking for not just the sign, but where the sign changes in that second derivative. So when we're looking at the steps, I'll give you kind of like the short version of the steps, but then add just some other details to them. The first step is, of course, you need to be able to find that second derivative. And when I say find that second derivative, we know that the second derivative is just the derivative of the first derivative. So you'll have your function, you'll find the derivative. Definitely, I recommend simplifying that first derivative. The more simplified your first derivative is, the easier your second derivative is to find. And then after you find your second derivative, you want to find where the second derivative is equal to 0 and where the second derivative is undefined. When we talk of increasing and decreasing, we call those critical points. We don't really have a special name for when the second derivative is equal to 0 and when the second derivative is undefined. We really just say that for the first derivative. So we just need to find where it's equal to 0 and undefined. Similar to the first derivative, if you have a fraction is equal to 0 when the numerator is equal to 0, the second derivative would be undefined when that denominator is equal to 0. And then step 3, we are going to make a sign chart with the second derivative. So basically, same steps as with intervals of increasing and decreasing, but instead of using the first derivative, we're going to use the second derivative. I think the harder part with concavity is not like the calculus, it's really just the algebra. So you have to think you have to do a derivative twice. So you have to be able to simplify correctly, and that's usually where I see the mistakes. It's not in like people don't understand defining when the second derivative is positive. The mistakes show up in like the algebra or again like the solving. So I was just going to do one example today, let you use the rest of the period to start homework, and then we'll kind of regroup tomorrow and do another example, and then Monday is just going to be a work day, and then your quiz is going to be on Wednesday. So first example is this. I'm going to make that a little bit bigger. So it says to discuss the continuity of the function, not continuity, concavity of the function. So we want to figure out the intervals of concavity. When is it concave up? When is it concave down? And then we also want to find the x-coordinates of any points of inflection. So we want to look at where that second derivative is going to change signs. So go ahead for me, since we're talking about concavity, go ahead and find the second derivative for me. So again, this is why you need to find the first derivative, simplify it if necessary. Then once you have the first derivative, take its derivative, and then that will be your second derivative. And make sure you're careful with the sign, positive or negative, when you're taking the derivative of that cosine of x. And so looking at your first derivative, the derivative of x squared becomes 2x. Then the next term, 4, is a constant multiple. The derivative of cosine is negative sine of x. and then the derivative of 10, that's a constant, so it goes to 0. That's your first derivative. You would use that to do intervals of increasing and decreasing. We're doing concavity, so we're going to take the derivative again. The derivative of 2x is 2. The derivative of sine is cosines. That negative 4 is just going to be a coefficient. We see trig, so sometimes we have to be careful about hidden denominators. This is cosine, which doesn't have a hidden denominator. So this was like tangent or cotangent, or secant or cosecant would have a denominator. This has no denominator, so the derivative is never undefined, but we do want to find when it's equal to 0. This is a trig one, so they give us an interval. We're going from 0 to 2 pi, so make sure we only find these key values from 0 to 2 pi. So we can go ahead and set this derivative, second derivative equal to 0, and then solve. Subtracting the 2, then dividing by negative 4, that's going to give you positive 1/2. Thinking about your unit circle, cosine is positive 1/2 at 2 places. One's in the first quadrant, one's in the fourth quadrant. I get pi over 3 and 5 pi over 3. So again, those are not called critical points, because those are only going to be talking about the first derivative. Those are just kind of key values. They're important values. And so from here, same process that we did yesterday. We're going to create a sign chart. Again, the sign chart is just a number line. This is a sign chart for the second derivative. We're going to put our key values on it in order. So my smaller one, pi over 3. And then I have 5 pi over 3. Since I have an interval in this one, I'm just going to put a 0 and a 2 pi on the end, just to remind myself not to put like negative infinity and positive infinity in my final answer. And then you do want to be careful. I sometimes see this mistake. People will, so this is about to be the wrong thing people will do, is they look at their second derivative and they'll put 2 and then this negative 4 cosine of x. So that is the wrong sign chart. Those are terms, not factors. So you just want to be careful with that. If I'm talking about factors for this one, you could factor out a 2 there, but it's really just one factor. So we just have a single row in our sign chart. We don't have 2 things really being multiplied. So it's just a single row. So we have 3 intervals, and we just need to figure out, is it positive or is it negative, basically. So plugging in just some values, go ahead and fill in that sign chart for me. And I would kind of think of maybe some easy radian values to plug into that. And then we'll go back and justify our question. Yes.
I can't do that, can I?
So if I'm plugging this in, so again, I can plug in endpoints when I do trig. So 0 for that first interval is pretty easy to plug in. 2 minus 4 times the cosine of 0. Cosine of 0 is 1, so 2 minus 4, that is negative. Anything between pi over 3 and 5 pi over 3 works. Pi is probably the easiest one to plug in. 2 minus 4 times the cosine of pi. Cosine of pi is negative, so that becomes 2 plus 4. So we have a positive interval. And I can plug in 2 pi for that last interval. 2 minus 4 cosine of 2 pi, that interval is going to be negative. Since we only have one factor, like those are the intervals we have, so I see the second derivative is negative, positive, and then negative. So now we have to remember that the sign chart is not our answer. Our answer is we have to clearly state the intervals and then our justification. So this was a function y, so I can say that y is concave down on the intervals. So from 0 to pi over 3, union 5 pi over 3 to 2 pi. How do I know it's concave down? Because the second derivative is less than 0. Where is it concave up? Y is concave up on the interval from pi over 3 to 5 pi over 3. How do I know it's concave up? Because y double prime is greater than 0. And then this also did ask us to find the points of inflection. So points of inflection are where the second derivative changes signs. So you want to make sure you still go to your sign chart. And I see at pi over 3, it goes from negative to positive. So pi over 3 would be considered a point of inflection. And then looking at 5 pi over 3, it goes from positive to negative. So it is also a point of inflection. So I can say something like y has a point of inflection at x is equal to pi over 3 and 5 pi over 3. I know those are points of inflection because y prime changes sign. I think one of the most common mistakes I see when it comes to points of inflection is students want to say that points of inflections occur when the second derivative is equal to 0, and that's not the case. You still need to always make a sign chart to make sure that it is changing signs. And I'll give you an example of that before I kind of finish out notes. But any questions on that problem? So again, not too bad. It's really the same stuff that we're doing with intervals of increasing and decreasing, except instead of using the first derivative, we use the second. The only thing I think is harder with these is sometimes once you find that first derivative, you do have to use your algebra to simplify it and then find the second derivative. So the last thing I did want to do kind of before I closed out notes. So when I'm talking about these points of inflections where I say students sometimes mess up at, I'm just going to make up an example. Say this is my sign chart I made for my second derivative. And again, I'm just going to make up, maybe you had key points at 0 and 2. I don't know what the factors are, so I'm going to say, like, say your sign chart went from negative, negative, and then positive. Students, for whatever reason, want to say that the points of inflection are at 0 and 2, but if this is your sign chart, only x equals 2 is your point of inflection. And you might look at me and you're like, well, duh, Mr. Brown, you just said points of inflection are where the sign changes, where the second derivative changes signs, and you know that, but then sometimes students just like don't make a sign chart and just stop at the values they solve for. So always make sure you make a sign chart, whether you're asked for the intervals of concavity or if you're asked just to identify a point of inflection. So that's all I really wanted to get done today. Your homework, I realized, did not put the problems that you're assigning in OneNote, but the problems you're doing for homework number 3 is 4 through 24 multiples of 4. Again, tomorrow I just have one problem we'll do is kind of just make sure we understand everything, and then you'll be able to work. Monday will be a review day. We'll kind of mix together intervals of increasing and concavity, and then your quiz is going to be that Wednesday between kind of those awkward, weird days of next week. So with that being said, I'm going to go ahead and let you get started with what you need to. Definitely let me know if you have questions as they come.